يكسر كسر الجيميل ID باندين بس ريموش
تم
نجمع ريكارد ستارت كده كم كسان يوتي ميل ID नहीं बस आते हुए ريموش
Okay, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Today this is our lecture number 2 of this course, and the topic of today's lecture is design of singly reinforced beam in flexure. Okay. So we'll be studying first of all the basic concepts of the design for a beam, and that is in flexure, not in shear. Topics to be addressed in today's lecture are behavior of reinforced concrete beam under gravity load, and then the mechanics of the beam under gravity load, and then ACI recommendations, design steps, and example. Okay, the objectives of the course are that at the end of this lecture, students will be able to explain behavior of reinforced concrete beam under gravity load, identify relevant ACI 318 code recommendations for RC beam, analyze and design RC beam for flexure. If I will run this animation, and you can see in the animation that beams are bending downward, the columns are also bending outward and inward. Because primarily the load will be acting downward, this is just for the purpose of animation that it goes up. Otherwise, it will come down. And if I stop it, when it goes down, we'll be able to see what happens when it comes down. It will be like this. So under gravity load, depending on the amount of load, the bending will increase with the increase in load, and the bending will decrease with the decrease in load. Anyway, if we exaggerate the bending of the bending shape of this frame, then you can see that the beam bends downward in the midspan of the beam, and then the beam does not come down or does not bend downward where it goes through the column, or it is supported by the column, in other words. Similarly, in the other span also the beam bends downward and till it reaches to the end where it meets another column at the end of the beam. So the beam, due to the support from column, does not come down or does not bend down, rather it bends upward. If you look at this shape of the beam closely, you will notice that the beam bends downward at the midspan, but the beam is being bent upward at the support or at the column. So the reason is that when the beam is unloaded, it will be straight. From end to end, it will be completely straight. Although due to its own weight, it will come down a little bit. But as compared to any superimposed dead load on the beam and live load on the beam, due to self-weight, it will be relatively straight. When it is loaded by some load, then the beam at the midspan will come down, or it will bend downward, or it will form a concave downward shape. Like you can see, a concave downward shape. When it bends downward and form a concave downward shape, you can see that the elongation will occur in the lower fibers of the beam, and the shortening will occur in the upper fiber of the beam. When elongation occurs in the lower fibers of the beam, it means that tensile stresses have caused this. And when shortening occurs in the upper fibers of the beam, upper portion of the beam, it means that there are some compressive forces, compressive stresses, which is causing this shortening. So from this, we can conclude that when a beam bends downward, there are compressive stresses in the upper part of the beam and tensile stresses in the lower part of the beam. The compressive stresses will shorten the upper part of the beam, and the tensile stresses will elongate the lower fibers of the beam. And there will be a section somewhere at the mid depth, depending on the situation, where there is no elongation or shortening, which is called as neutral axis. I hope you know these things and you would have studied this in some of your courses. Now, what happens at the support where the beam crosses the column? Since the beam is being supported by the column, it cannot come downward on this at this location. So when the beam comes downward at the midspan, the beam at the location where it meets the column or where it is supported by the column will be basically in its initial position. It cannot come down. But since the remaining beam has come downward, so this part of the beam will be, if this is to be part of this beam, as long as it is part of this beam and it has not collapsed or failed, so the remaining portion of the beam which is supported by the column will be little bit will bend upward like this. Will bend upward like this, and unlike the midspan of the beam, the tensile stresses will occur in the upper part of the beam at the support, and compressive stresses will occur in the lower part of the beam. So it is quite opposite to what is happening at the midspan in the beam. So if, for example, from the last lecture, I hope you know now that wherever there are tensile stresses, you will be placing some reinforcement, and in the reinforced concrete, we will be placing reinforcing bars or rods, steel rods or bars. So these steel rods will be placed on the lower side of the beam at the midspan, but these bars will be placed at the upper side of the beam where the beam crosses the support or where the beam is meeting the column. Because the elongation occurs in the upper fiber, because the beam will come down, it will stretch this part. When this part is stretched, so this upper part of the beam will be in tension, in the lower fiber of the beam will be in compression. So if you place longitudinal bars or tension along the length of the beam, you will have to place these bars in the lower portion of the beam at the midspan, and in the upper portion of the beam on top of the column. So this is a basic difference in the behavior of the beam, two-span beam. However, if it is a single-span beam, simply supported beam, then there will be no tensile stress in the upper part of the beam. There will be only compressive stress in the upper part of the beam all along the length of the beam, and there will be tensile stress in the lower part of the beam. If you want to draw a bending moment diagram for this beam, I hope you can draw a bending moment diagram for this beam very easily. You will have positive bending moment at the midspan and negative bending moment at the column. So the shape of this, the shape of the bending moment diagram for this beam will be like this. I hope you know this. Can you see this bending moment diagram?
Yes, sir.
I hope you agree with me that bending moment diagram for the beam will be like this if it is subjected to uniformly distributed load. So you can see that there is a positive bending moment at this location, and we have a negative bending moment at this location. So the positive bending moment basically will cause tensile stress in the lower fibers of the beam, and negative bending moment will cause tensile stress in the upper fiber of the beam, because the direction of the bending moment is different. That's why the direction of bending moment is different. And there will be location where there is no bending moment. This location is the point of contact flexure, a point of zero bending moment. So at this location, basically the bending moment is zero. This location, the bending moment is zero. But after this location, the bending moment direction changes and it becomes negative from positive. When the bending moment changes its direction from positive to negative, then the stresses location will also change. In the midspan, corresponding to positive bending moment, tensile stresses are occurring in the lower part of the beam, but in negative bending moment, the tensile stresses will occur in the upper part of the beam because the beam bends up. The beam does not basically bend upward, but the beam is at its original position, and because the beam is one, the beam is all the beam is made of just one material. Imagine this is made of rubber, for example. If you imagine that it is made of a rubber material, when it comes downward, so this will stretch the fibers at the support of the beam, and the beam cannot come downward at the support where it is supported by the beam. So the upper fibers will be stretched upward and the lower fibers will be shortened. So in this manner, you can also compare the direction of tensile stress with the bending moment. Whenever there is a positive bending moment, so you can say that the tensile stresses location is in the lower fiber of the beam. And whenever there is a negative bending moment, the tensile stress will be in the upper fiber of the beam. For this reason, whenever we place reinforcement in the lower part of the beam due to positive bending moment, we call this as positive reinforcement. And whenever we place reinforcement in the upper part of the beam due to negative bending moment, we call this reinforcement as negative reinforcement. Correct? Okay?
Yes,
Yes,
sir.
sir.
We can move ahead now. I will show you now a actual beam which has been tested due to which has been tested under a point load, and the point load was applied at its mid-span. This was the students' project, final year project. The students captured this video, recorded this video. They had their final year project in order to see what happens to a beam under a point load or under a gravity load. Okay, so a beam can be subjected to a point load, uniformly distributed load, just to see what happens when the beam is subjected to a point load. I will show you this video. You will be able to see that as the test progresses, the beam undergoes different stages, and finally the beam fails. So you should watch this video carefully, and also note down if something is not clear to you. Note down your questions, and then I can answer your questions at the end of the video. Okay. The length of this beam which is being tested in this video is 7 feet, and you should remember that this beam is basically a beam which has been properly designed according to the ACI code for flexure as well as for shear. So this is a properly designed beam. Properly designed beam. The depth of the beam is 12 inch. The width of the beam is 8 inch. If you want to note down these dimensions, you can note down width of the beam is 8 inch, depth of the beam is 12 inch. So it is 8 by 12 inch beam. The length of the beam from support to support is 7 feet. Number 4 bars. I hope you know what a number 4 bar is. It is half inch, 4 by 8. So 4 half-inch round bars have been placed as longitudinal reinforcement in the lower part of the beam because it is a simply supported beam. So now you know that tensile stresses will be produced in the lower part of the beam. So the beam has been reinforced with steel bars, 4 number steel bars having a diameter of half inch. The strap spacing you have seen in one of the videos in the last lecture that there were stirrups in a beam. Those stirrups in the beam, in this case, they have been placed at 5 inch center to center. And the calculated load capacity due to the ACI code equation is 90 kilonewton. However, when the beam is tested practically, it may not give you exactly this capacity because this is a calculated load capacity from the equation. You will learn these equations today. When the beam is actually tested, there will be difference in the calculated load capacity. Normally, when a beam is tested, the testing load capacity will be greater than the calculated load capacity because there are many safety factors in our design process. So actually, you will get more load capacity than the calculated load capacity. Correct? So with this, I will run this video now. You can watch the video, pay attention to this, and try to note down your questions, and then we can discuss the questions. Right. This beam has been tested under a point load, as I said earlier. The deflection under the load are also being noted, and a plot between load and deflection is also drawn as the load progresses. The deflections are noted corresponding to an increment of 5 kilonewton, which means that when the load is applied continuously, each 5, 10, 15, 20 kilonewton, the deflections are noted. The deflection This is first thing to note down, that although the load has been applied in the beginning, there are no cracks. And the engineer who is testing the beam, he's looking for some crack with the help of magnifying glass, which means that the cracks may be very narrow, and he will not be able to see the cracks with the naked eye. That's why he's using a magnifying glass to note any crack. And you can also note down that in the beginning there is no crack. Okay, as the load, as the test progresses and the load is increased, so crack will appear. You can also see load versus deflection plot, and in the beginning load is directly proportional to deflection, which means that at every increment of the load, there is an equal increase in deflection. So load and deflection are directly proportional. However, when cracks appear, substantial cracks appear in the beam, then this proportionality will still be there, but it will not be linear. There will be non-linear proportionality between load and deflection. I will show you the video once again. Okay, you can see that this person who is testing the beam is writing down some value on top of the crack. This is a general practice in testing that the load at which the crack appears is written on top of the crack. So he's basically noting down the value of the load at which the crack, that particular crack appears. Okay, so now we can discuss some important concepts, and this video will help us in understanding those concepts. Okay, we have seen a beam being tested under a point load P. Okay, the length of the beam was 7 feet in the test, and the section of the beam was such that width of the beam was 8 inch in depth 12 inch, 8 by 12 inch beam. Okay, and you have seen that the beam undergoes many stages. In the beginning, there was a stage where there was no crack, although the load was there. Okay, so in the beginning, when the load is applied up to some value of the load, no crack was noticed. And then cracks started appearing in the lower part of the beam, not in the upper part of the beam. And the reason for this is that when the beam bends downward, the upper fiber of the beam will be compressed, and the lower fiber will shorten or will elongate. The lower fiber will elongate, and you know that elongation is being caused by tensile stresses. Okay, and if you draw a bending moment diagram for this beam, it will be a triangular bending moment diagram like this, which means it is a positive bending moment, and as I said earlier, a positive bending moment will cause tensile stresses in the lower fibers and compressive stresses in the upper fibers. You know that concrete is weak in tension, so tensile stresses in the opposing direction like this will produce a gap here at this location. These tensile stresses. It's just like when two different objects are glued together and you want to pull them apart. You can pull them apart with applying two opposing forces. And when you apply the force at certain value of these opposing forces, the material will break at that location of the glue. So it's somewhat similar to that example, that this concrete different parts have been glued together with the cementing paste, and when tensile stresses are produced in the beam due to the load application, these tensile stresses in the opposing direction will cause cracks, and the crack must be vertical because the load is applied in the horizontal direction, in the direction along the length of the beam. So when the forces are along the length of the beam, the crack must appear in perpendicular to this, because the crack is basically a gap. A gap appears at this location when you try to pull this part of concrete. When the stresses are applied due to the application of load, so these stresses will pull this part of the concrete in the opposing direction and will produce a gap at this location. When the tensile stresses exceed the tensile strength of concrete, so concrete will fail, or the concrete will fail due to the application of these forces, and a gap or crack will appear in the direction perpendicular to direction of the stresses. Okay, so then when the load was increased progressively, the cracks were appearing and they were moving upward, with the incremental increase of the load. Okay, and they were. So why these loads were moving upward? Because initially the crack appeared in the bottom portion of the beam, because if you look at the stress strain variation of this beam, you have maximum tensile strains in the bottom of the beam. So the maximum tensile strain, according to the flexure equation, if you know this equation, it was F is equal to my by I, and it is quite true in the linear elastic range. Bending moment is maximum at this location under the load P, and Y is the neutral axis depth from the Y is the depth of the tensile stress location to the lower fiber of the beam. So this is this distance Y. So when Y is maximum and M is maximum, M is maximum beneath the load and Y is maximum in the extreme bottom fiber. So a crack must start to appear in the bottom portion of the beam, because I is constant, I is moment of inertia. Okay, when the load is further increased. So with a further increase in load, the strain in this location will also exceed a value, at which concrete cracks. And that value is in the terms of strength, is the tensile strength of concrete. When the stress in concrete exceeds the tensile strength of concrete, a crack will appear. And this crack will appear with progressively increasing the load. When the load is progressively increased, the tensile stresses will keep on also increasing in the beam, and these tensile stresses, which were in the beginning in the bottom fibers, in the bottom of the beam, your maximum, with the progressive increasing of the load, these tensile stresses will also keep on increasing, and this shape of the stress diagram will also change like this. Will keep on changing like this. So you can see that initially when the stress was equal to this, now even in the other portion, the stress is this. These are the stresses, and the strains. So the stresses and strain, they will keep on increasing in the lower portion of the beam, and as soon as the value of the stress in the lower part of the beam exceeds the tensile strength of concrete, a crack will appear. So the crack will slowly and gradually keep on moving upward with the increase in load, because in the portions of the beam on the lower side of the beam, the tensile stresses will also keep on increasing with every incremental increase in the load. Okay, and when this happens, you can see that the neutral axis will also shift upward. Neutral axis will keep on shifting upward. And this neutral axis will keep on shifting upward. So initially, when neutral axis was at the mid depth, this neutral axis will also keep on shifting upward. Finally, it will become, the neutral axis will be very close to the compression zone. Okay, this was happening in the tension zone. What was happening in the compression zone? Shortening was occurring in the compression zone. And you have noticed that cracks appeared only at the final stage in this compression zone, at a very, very final stage in this compression zone. So this neutral axis will basically will go out of this diagram. This neutral axis will go out of this finally at failure, and crushing of concrete will occur at the top portion. And if there was a couple with C in the top portion and tension T in the lower portion, so this couple will basically will cease to exist in the beam, because this couple is going to resist the bending moment C and T, compression in the upper part and tension in the lower part. So this will, okay. Since we have placed reinforcing bar in the lower part of the beam, and that's why the beam was capable of resisting a lot of load and a lot of bending moment. In other words, had there been no reinforcement, what would have happened? If there had been no reinforcing bar in the lower part of the beam, a crack would have appeared in the very beginning, and the beam would have split into two pieces. This crack would have appeared and would have crossed the beam in this manner, and the beam would have split into two pieces in the beginning, at a very low load as compared to the final load, which we have noted in the corresponding to the crushing of concrete in the upper part of the beam. So if there is no reinforcing bar, then the load carrying capacity of the beam will be very small, and this beam load carrying capacity can be increased by placing reinforcing bar. However, the crack's appearance cannot be controlled by placement of reinforcement. This you have noticed, because the reinforcing bar is still there, the cracks have appeared. However, in the very beginning, or when the loads are very, very low as compared to the final load at which the beam will crush or the beam will fail, there will be no cracks. But when the load is increased, the cracks appear in the beam. So from this you can learn and you can understand that the appearance of few cracks in the beam does not mean that the beam is going to fail, because there were a lot of cracks in the beam and the beam was still capable of taking a lot of load. And finally, there was crushing of concrete in the upper part of the beam. So few cracks appearance in the beam does not necessarily mean that the beam is going to collapse or the collapse of the beam is imminent. So you can learn these things from this video. And you have also seen that the beam undergoes different stages. In the next coming slide, we will be studying three distinct stages of the beam through which the beam undergoes. There will be a stage where there was no crack. This will be our stage number 1. And another stage is a stage where the steel, where concrete in the lower portion of the beam is cracked substantially, but concrete in the compression zone is still intact with no cracking. And there will be a third stage corresponding to the final stage where the steel has yielded and concrete has crushed in the upper zone. Okay, so we will be studying these different stages now one by one. If you have any question, you can ask your question. Otherwise, we will go ahead with the discussion on these stages. Please ask your questions if you have any questions.
सर ये जो क्रैक्स अपीयर होते हैं ये सिर्फ बीम के सरफेस पे अपीयर होते हैं कि ये इनटू द बीम भी प्रोपेगेट करते हैं सर?
नहीं, ये बीम में पूरे प्रोपेगेट होते हैं, पूरे सेक्शन में होते हैं, सरफेस पे नहीं होते, पूरे सेक्शन में दोनों साइड पे होते हैं। मतलब बीम को,
ठीक है सर।
हाँ, दो, ठीक है
सर। और सर दूसरा क्वेश्चन ये कि सर हमने जो अभी टेस्ट देखा वीडियो में, ये तो हमारे पास फ्लेक्सर फेल्यूर हुआ ना सर, तो हमारे पास फेल्यूर जब होता है तो वो किस तरह होता है?
वो डिफरेंट होता है, वो शेयर लेक्चर में पढ़ेंगे इंशाल्लाह। ठीक है,
ठीक है सर।
Any other question? You can also do some final year project if you are interested and a similar testing. In this project, the strains were not calculated, but we have strain gauges. With the help of strain gauges, you can exactly calculate the strains, and you can plot these tests and these strains throughout these different stages. So it will be very interesting to see. People have done this, but if you do this, some of you can do this project that they test few beams and then place inside the beam some strain gauges and record the strains, plot the strains through which corresponding to different stages through which the beam goes during the testing process. So it will be very interesting to see these strains. Okay, strain in steel and strain in concrete, in the compression and the tension zone, and you can plot these strains. Okay, for a different situation. So it can be a good project for you to learn more about this internal mechanics of the beam. Okay, what is internally happening in the beam? This is called internal mechanics. Okay, so let's move ahead now. As I said earlier, the beam undergoes many stages, but for the purpose of discussion, we have selected only 3 stages. These stages are quite distinct and different from one another. In stage number 1, is a stage corresponding to uncracked concrete, and this is an elastic stage. And this is quite obvious, as you have seen in the video, that it loads much lower than the ultimate. Ultimate means the load at which the beam finally collapsed or finally failed. Concrete remains uncracked in compression as well as in tension, and the behavior of the steel and concrete both is elastic. So this is the stage at which no crack appeared primarily. No crack appeared. So this is no crack stage, neither on tension side nor on compression side. And everything is perfectly stable and intact, and there are no cracking, and both the material, concrete and steel, are in elastic stage. Okay, this is the stage number 1. Stage number 2 is a stage where concrete has cracked in the tension zone and but remains uncracked in the compression zone. So this is another stage, and concrete in compression and steel in tension both behave in elastic manner, because the load is such that concrete in compression is still in the elastic stage. If you have seen a plot for concrete between stress and strain, and you can see that this is a curve like this. It is a curve between stress and strain in concrete like this. So when loads are in such a range, in this range, which is around 50% of its, if this is FC prime, this is FC, and these are strains. So this is basically when FC is FC by 2, this FC by 2, the stress and strain, the stress in concrete is proportional to strain. and then it becomes non-linear. It becomes inelastic and non-linear. Inelastic means that it cannot be recovered, okay, when you remove the load, okay. And so this is the stage, and steel is also in the elastic stage, which means that the steel has not yielded. So steel is also at this somewhere at this stage, yielding, because the yielding, when yielding occurs, then there will be inelastic behavior of the steel, and up to yield there is elastic behavior of the steel, which means that if you remove the load, you can completely recover the strains. Okay, then there is a final third stage where concrete is cracked in tension, and this is a stage already occurred. This is a situation which has already occurred in stage 2, and then concrete in compression and steel in tension both enters into inelastic range. At collapse, steel yields and concrete in compression crushes. So basically, if we draw stress strain curve for concrete, so concrete is somewhere here in this stage, and steel is here in this range somewhere, okay. This is Fy and this is Fc prime. So concrete on the compression side, because in the tension side, concrete is already cracked. With further increase in load, concrete in the compression will crush or will crack, and steel will also yield. Okay, either, so there is a question whether these two material will reach their inelastic stages simultaneously, or which material will reach first and the other next. This is a question which we will answer in the coming slides. It is possible that both material, I mean to say that concrete in the compression zone will crush and steel will yield simultaneously, or concrete can crush before steel yields, or steel can yield before concrete crushes. So these are three possibilities. These three possibilities we will discuss, okay, because it's important to understand that what happens finally. Okay, now we will derive equations for these three stages one by one. This is stage number 1. You should look at this stage number 1 carefully. This is stage number 1. Load lower than the ultimate, much less than the ultimate. So what will happen at this load? You can see this is the internal behavior of the beam. Internally inside the beam, there will be compression stresses. Compression stresses in the upper part above the mid depth or above the neutral axis. Above the neutral axis is at mid depth in an uncracked beam. But then the neutral axis will keep on shifting upward with the increase in load, okay, and the compression zone will keep on decreasing, and the tension zone will keep on increasing, okay. So as you've seen in the test. So in the beginning, when there is no cracks, the neutral axis is at mid depth, which means there are no stresses. If you look at this stress diagram, so the stresses in the upper part are maximum in the beam. These are compressive stresses, okay, and these stresses are gradually decreasing as we go downward along the depth of the beam, and then the stresses become zero at the mid depth, and then the stresses direction changes to tension, because in the lower part of the beam there will be tensile stresses. So the tension stresses and then slowly and gradually keep on increasing till the maximum tensile stresses occur at the extreme lower part of the beam. So there is an increase in the tensile stresses from bottom to the neutral axis, and from top, and in the compressive stresses from top to the neutral axis. Okay, so if we now, this is not the beam that has collapsed. You should mind that the beam, when the two portions of the beam were separated in this animation, it does not mean that this is the situation corresponding to the separation of the beam. This is by this, okay, when the load is applied. So when we remove this, when we detach, basically we are detaching one part of the beam from the other, just to show you what happens internally in the beam. This is not the collapse of the beam or cracking of the beam. So when the load is applied and there is no cracking, this will be the internal situation or internal stress state. Internal stress state. Internal stress state or stress situation. Internal stress state or situation. What is happening internally in the beam? So internally in the beam, compressive stresses are maximum in the upper fibers, and they are slowly, gradually decreasing till the mid depth, which is neutral axis. Tensile stresses are then produced, and the tensile stresses are also increasing till they reach their maximum value in the bottom of the beam. Okay. So now if we, okay, you also know that you can represent the stresses with a force C. In the upper part, we have compressive stresses. So we can represent these stresses with resultant C, and resultant C is a force basically. You know that stress is equal to stress S is equal to P divided by A. Stress is equal to P divided by A. So if we say that in the upper portion the stress is Fc, in the top portion Fc maximum, and this Fc is gradually decreasing till we reach the mid depth, this will be equal to C divided by A, where C is the resultant compressive force. Then this resultant compressive force will be C is equal to Fc times A, Fc times A. But then the Fc will be average Fc, because we have maximum Fc at the extreme top fibers and 0 here. So the average Fc will be Fc plus 0 divided by 2. So this will be Fc divided by 2. So you can represent this in the compressive force by this diagram with the C equal to Fc divided by 2 multiplied by A. Okay. What will be the area? The area will be the half of the area on which this compressive force is applying. This half of the area of this half of the top area, this area. This will be the area. So C will be Fc divided by 2 and multiplied by the area, and this area is half of the area above the mid depth. So this is BH by 2. If total depth is H and the width is B, this will be BH by 2. So this will be. Similarly, T can also be shown by these equations, similar to this. So you will now further study this thing. It will happen like this. Okay. And if you now start looking to this diagram from a side, so in two-dimensional plane, so you will see a diagram like this. Compression and then tension. Okay, like this. But it is a general practice. It is a general practice that these diagrams are drawn on opposite side like this. This diagram is drawn on the other side like this. So this is C and this is T. This is a general practice. Okay. So now you will see this diagram like this. The same diagram, only the tensile stresses have been shifted from this part to this, from this side to this side. So we have compressive stresses in the upper fibers, tensile stresses in the lower fibers, the maximum compressive stresses in the top fibers, top extreme fiber, the maximum tensile on the lower most fibers of the beam. This is a stress diagram. Stress is perfectly proportional to strain at every location. This is depth of the beam, effective depth of the beam. Okay, effective depth of the beam is the depth from the top fibers of the beam to the centroidal axis of the reinforcement, if there are reinforcing bars. If we place reinforcing bars in the lower part of the beam, then from the top portion of the beam to the centroidal axis of the reinforcing bars, the depth is called as effective depth. This is called effective depth. This G is called as effective depth. The total depth of the beam is H, and the width of the beam is V. And the lower part of the beam is called as is in tension, so this is called as tension zone. The upper part of the beam is in compression zone. And this is a stage where concrete is at the verge of failure in tension. So this is just before the crack appearance. So any increase in the load beyond this stage will cause a crack in the beam on the tension side. The situation in this, okay, if we compare now this compression zone in which concrete is in compression with the stress strain diagram of concrete. So you know that the stress strain diagram of concrete will be like this, and the stress, the extreme stress, the stress in the extreme fiber, the FC, on this stress strain diagram will be much lower value, much lower, somewhere here, much lower value, because this is the final failure of the beam. This is FC prime. So this value of FC is quite less than FC prime. is quite less than FC prime. So we are here on this stress strain diagram. And on the tension side, because concrete is very weak in tension, concrete will fail or will crack at this location. So it is at the verge of cracking. We are at the verge of this. FT is just equal to the modulus of rupture or the flexure tensile strength. And in the last lecture, if you remember, we said that the flexure tensile strength of concrete can be determined by 1-point load test. And according to the ACI code, generally the flexure tensile strength of the beam is taken as 7.5 times FC prime. If you remember, I told you in the last lecture that the flexure tensile strength or modulus of rupture can be represented in terms of square root of FC prime. So according to the ACI code, this modulus of rupture are the flexure tensile strength. Flexure tensile strength of concrete is 7.5 times FC prime, so it's square root of FC prime. If you can calculate this value, you will notice that this value comes out to be around 8 to 9 times less than 1 by 8 to 1 by 9 of the compressive strength of concrete. If we calculate this value for FC prime 3000 psi, can you give me the value of FT corresponding to FC prime is equal to 3000? Please calculate this value and tell me what is the value of FR or FT. It is again, listen, this is a flexure tensile strength, flexural tensile strength of concrete beam. Okay. FC prime 3000 square root of FC prime 3000. So the value comes out to be around 410 psi, 410 psi. Okay. In KSI, it comes out to be 0.4 KSI. Right?
FC prime sir 3000 है
3000.
yes
sir 410
410.8
Okay. Now we will try to derive equations corresponding to this stage. Okay. What is our purpose of all these equations? Our purpose of all these equations is to know the capacity of the beam in this stage, which shall be equal to or more than the demand coming on the beam. You have seen in the beam, you should pay attention to my statement. You have seen in the beam, there was a load P. What this load P was causing to the beam? This load P was basically producing bending moment in the beam and also shear forces in the beam. Okay, at the moment we are not discussing shear forces, we are discussing just the bending moment, because bending moment is caused by the application of the load. And the bending moment further produces stresses in the beam, compressive stresses in the upper part of the beam and tensile stresses in the lower part of the beam, right? And the combination of these two stresses are called as flexure stresses, because they're also called bending stresses because these stresses are produced due to bending of the beam, right? Okay, now before we move ahead, I will give you one beam which is simply supported. Okay, let's say we are talking about the same beam which we were testing. The length of this beam is, you have seen, was 7 feet, and the depth of the beam was 12 inch, and the width was 8 inch. Okay, and there is a load P. What will be the bending moment, maximum bending moment for this in terms of, this will be P by 2, reaction, P by 2, and the bending moment M, maximum bending moment, will occur at the mid-span, you know, will be like this. And this value will be equal to P by 2 into L by 2, so this will be PL by 4, correct? Okay. Okay, now this is important to note that this bending moment is produced by the load P, correct? If load P is 0, there will be no bending moment. And this bending moment is applied bending moment, or we can also call this bending moment as demand bending moment, because the load P has produced this. The load P has produced this. Let's say there is a certain situation. There is a certain situation in which a 7 feet long beam with this dimension has to bear this load for some situation. Let's say we are keeping some sandbags here, some sandbags for some, because there is a need. There is a need to place some sandbags here for some purpose. Okay, and this load of the sandbags or whatever the load is, it will create a load P at this location, and this load P, when pushes the beam downward, will create bending moment M, and this bending moment M has been calculated in this manner. Correct? Okay. Now, internally, the beam must resist this bending moment M. Internally, the beam must resist this bending moment M. If the internal bending moment of the beam is greater than this M, at any particular stage, the beam will not fail, the beam will serve its purpose. However, as soon as this M, which is coming from this load P, exceeds this resisting moment, when you keep on increasing the load, with every incremental increase in the load P, M will keep on increasing. And there is a fixed resisting moment of the beam. The resisting moment of the beam, as you will see now, comes from the geometry and from the material strength. Okay, so and as you know that the geometry of the beam is fixed, because the beam is 8-inch wide and 12-inch deep, and the strength of concrete is the strength of the material. So strength of material is fixed, the geometry of the material is fixed. There will be a fixed value of the resisting bending moment, and as soon as this Mx exceeds the resisting bending moment, then the beam will crack or the beam will collapse. Is the situation is, you will see in the discussion now under stage number 1. So this is a demand. This is the demand which is coming from the load. This is an external thing. This is an external thing, because if there is no load P, there will be no bending moment. So this is external thing. This external thing is causing a bending moment in the beam, which we can calculate from the bending moment diagram. And this external bending moment must be resisted by an internal couple. And we have seen that there was a C and T here, C and T. This C and T internally will produce a couple in this direction, and this is the internal couple or internal bending moment which must resist this Mx. If this internal bending moment is less than this Mx, then the internal couple will cease to exist, and the beam will collapse. Because if there is no internal resisting bending moment, then the beam will collapse and the beam will fail. Okay, so how this couple can cease to exist? This can cease to exist if concrete crushes. If concrete crushes, there will be no C, because there will be no resistance. There will be only T, and the couple, the resisting moment will cease to exist. Or if concrete cracks in tension side, let's say there is no reinforcing bar. So in concrete exceeds this tensile, the stresses in concrete exceeds tensile strength. So this T will not be resisted now. So T will cease to exist. When T ceases to exist, the couple will not be there, and the beam will fail. So either T or C ceases to exist, then the beam will fail. We have seen now several times that concrete is very good in compression, so C will not cease to exist. C will be there, but T will cease to exist. T will cease to exist because the concrete is weak in tension. So when stresses in concrete reach the tensile strength of concrete, T is no more there. When T is no more there, the couple will cease to exist, and concrete beam will fail. Now, when we place reinforcing bar here, although concrete has cracked and concrete has failed, but then the steel will take playing its role. the steel will start playing its role, and all the tensile stresses will be now resisted by steel. So there will be T here in terms of the resistance offered by steel, and C there in the concrete. So C and T will be there when a reinforcing bar is placed inside concrete. Although concrete is cracked, but then steel will play its role in resisting tensile stresses. So C and T will be there, and you have seen in the test that when we were slowly and gradually increasing the load, although concrete was cracking more and more, but since steel was there, steel was yielding, C and T were there, and the beam was not collapsing or the beam was not failing because the couple existed till the end of the test. So this is an enough explanation which I think is very, very important to understand the internal behavior of the beam. Now, corresponding to stage number 1, we can derive equation where we can derive equation for MR, resisting moment, corresponding to stage number 1. You should remember once again, you should pay attention to this, write down that the applied moment or the demand moment is coming from the load. When the load is applied, so it will produce bending moment, and you can calculate that bending moment from the bending moment diagram very easily and very conveniently. And you should also note down that it is regardless of the material of the beam. No matter the beam is made of concrete or made of steel or made of any other material, this bending moment diagram, this bending moment which we obtain from bending moment diagram is always there, regardless of the material from which the beam is made. So this bending moment is coming from the load. This bending moment will be there, and this bending moment shall be resisted internally by the beam. And we are going to now investigate the beam internally in order to calculate that resisting moment. Okay. So we have one bending moment coming from the load, and another bending moment should come from the internal couple, and you have seen that there is a C here, which is the resultant compressive force in the top portion, and then you have a T here, resultant tensile force. And as I said earlier, C will be equal to what? C will be equal to, if this value is Fc and this value is 0, so this will be average stress, Fc divided by 2, Fc plus 0 divided by 2. Fc plus 0 divided by 2 is average stress, because you know that P is equal to S into A. P is equal to S into A. So this will be C is equal to S into A. And S in this case is average stress, because the stress is not uniform over the area A. What is the area A? The area A is half of the area of the beam. If you take a section of the beam, cross section of the beam, so this half area is in compression. This is H by 2, and this is B, right? So this will be BH by 2. Similarly, T will be equal to Ft plus 0 divided by 2 into BH by 2. Correct? Because the half of the portion of the beam is in tension. This is in tension. This is tension zone, that is compression zone. When we equate C equal to T, so everything will be cancelled except Fc and Ft. So which means that Fc must be equal to Ft. If this is Ft, Fc must be equal to Ft at this stage. We are talking about stage number 1. You should mind it. We are talking about stage number 1. And we know that there are some steel bars here at this location. There are some steel bars here at this location, but those steel bars have been ignored at the moment, because the stresses are very, very small, and in these very, very small stresses, the contribution from steel bars can be neglected. Or in other words, we can treat this beam, although it is a reinforced concrete beam, we can treat this beam as if it has been made of plain concrete without reinforcement at this stage number 1. At stage number 1, when the stresses are very, very small, we can treat this reinforced concrete beam as if it is a plain concrete beam. So there is no contribution from steel. Otherwise, if there is a contribution from steel, the T must have been written like this: Ft plus 0 divided by 2 into BH by 2 plus some steel contribution, ASFS. But since this Fs will be very, very small, Fs will be almost equal to 0. So this terms become 0. And the situation becomes as if it is a beam with no reinforcing bar in stage number 1. In stage number 1, when no crack has yet appeared. Okay. What will be the resisting couple now? The resisting couple will be equal to MR, either C multiplied by this lever arm, or T multiplied by this lever arm. Okay. But we are not interested in C, because C concrete is good in compression. We are interested in T, because T will basically govern or will give us the capacity which we want to calculate, and we want, because concrete will crack in tension, not in compression. So we want to calculate the lowest capacity, because if you calculate the capacity from C, so it will give you a very good capacity, but concrete is weak in tension, and the beam will fail in tension instead of in compression. So we must have to calculate MR from T, not from C. So it will be T multiplied by lever arm, and lever arm will be equal to what? How much? If the total depth is H, so you know when the resultant C, the location of the resultant C will be H by 6 from top, because if this depth is H by 2, you know that from the triangle, the largest side of the triangle, the resultant C will occur from this distance, and this distance from this distance is H by 2, and 1/3 of this distance will be H by 6. Similarly, from bottom, if this distance is H by 2, so this distance, which is the point of application of T, will be H by 3 of H by 2. So this will be H by 6. H by 6 and H by 6. So the lever arm will be how much now? H minus H by 3. So it will be 2 by 3 H. Lever arm. So this lever arm, this will be equal to T into 2 by 3H. Correct? This MR equal to T into 2 by 3H must be greater than this Mx. Must be greater than this Mx if the beam is not to fail. Okay? As I said earlier, that at the moment we are ignoring the contribution from the steel bar. So let's treat this beam as if the beam is made of plain concrete. So when we say that T into 2 by 3H, so T basically is contribution from concrete alone. T multiplied by 2 by 3H, we will substitute this value of T now. This is the value of T. Ft divided by 2 into BH by 2. Substitute in this equation for MR. You do it yourself. It will be Ft divided by 2 into BH by 2 into 2 by 3H. So what will be MR equal to? What will be MR finally equal to? Ft BH square by 6. Correct? Okay. If you substitute the value of T in the equation for MR, then Ft by 2 into BH by 2 multiplied by 2 by 3H will give you MR equal to Ft into BH square by 6. Okay?
Yes, sir.
Okay, so we can move ahead now. MR will be now equal to, MR we calculate here, it will be equal to FT B square by 6. Okay, now let's say we want, I ask you that calculate MR. Let's say I ask you to calculate MR, so that we exactly know what is the capacity of this beam. Flexure capacity. This is the flexure capacity or bending capacity. This is called bending capacity or flexure capacity, but corresponding to stage 1. Should also write down this, corresponding to stage 1, at stage 1. Okay. So MR corresponding to stage 1 is FT into B square divided by 6. If I ask you to calculate this capacity for the beam, which we were discussing or which we tested, so you know that the beam is 8-inch and 12-inch. Can you calculate the capacity of flexure capacity of the beam corresponding to stage 1 if I ask you to do this? Please start doing this. Calculate MR. What is FT? What is FT?
Sir, 14.8.
G? What is FT? What is FT? I didn't ask the value of FT. What is FT?
Tension stress, sir.
Tension, sir.
It is not tension. FT is not tension.
Flexural tension. Flexural tension.
It is not tension. It is flexure tensile strength.
Strength है sir, strength.
There is difference in tension and tensile strength. Tension is where you are in tension in examination. That is your tension, because you are stretched a little bit in examination. Okay? But this is flexure tensile strength. It is your capacity to resist this tension that you undergo in examination. So this is flexure tensile strength or modulus of rupture. Okay, and I told you that this FT or flexure tensile strength, according to the ACI code, is 7.5 times FC prime. If FC prime is 3000 psi for this beam, for concrete used in this beam, then now you can calculate MR very easily. Tell me the value of MR.
Sir, 78.8.
78.8. FT is equal to how much? First, give me the value of FT.
Sir, 410 psi or 0.41 KSI.
Okay, we will be working in KSI. Okay, so let me write this value in 0.41 KSI. Correct. Now calculate MR. MR is equal to 0.41 into 8 into 12 power 2 divided by 6.
$78.72.
What? Always use units.
Sir, keep inches.
Keep inches. Correct. So it is 78.72 Cape inch or inch Cape. Okay. Now, if I ask you to calculate the maximum point load, to which this beam can be subjected, if it is made of plain concrete without reinforcing bar, can you calculate that load P? And if yes, how?
Yes, sir.
How?
सर PL/4 का फार्मूला यूज करके उससे फाइंड कर सकते हैं
कैसे फाइंड करेंगे, जरा मुझे स्टेप बताओ।
सर मूवमेंट इज इक्वल टू PL/4, तो अगर हम उसमें P एक अननोन है, हमारे पास लेंथ भी है और MR भी है, तो इससे P फाइंड कर सकते हैं।
नहीं, कैसे? एल आपके पास है, चलो तो फिर भी अननोन है। मैं तो P कहता हूँ, P मालूम करो ना, M तो मालूम नहीं है।
तो M हमारे पास ये रेजिस्टेंस कैपेसिटी, हमारे इतना रेजिस्टेंस कर सकते हैं।
Yes, this is the answer that I was expecting. That this MR, M which is coming from the load, this is PL/4. This is very, very important to understand at this stage. This is coming from the load, okay? And the maximum capacity of this beam in bending is MR, so they must be equal. This MR must be either greater than this PL/4, okay? And then the beam will not fail, or at least this should be equal to this. If I ask you that you are, let's say you are taking in a load weightlifting competition, and your capacity of lifting a weight is 100 kg, and the weight is also 100 kg. So you will successfully lift the weight. But if the load is, theoretically speaking, if the load is 100.1 kg or 101 kg, then you will not be able to lift the weight, at least theoretically speaking. Okay? So when MR is at least equal to PL/4, this beam, which is in this particular case, we assume that it is made of pure concrete, plain concrete, will not fail as long as MR is greater than or equal to. So let's say MR is equal to PL/4. So when we say MR is equal to PL/4, the beam will not fail, and we can calculate the P value like this: PL/4 equal to 78.72 Kip inch, and then find out P now. L was 7 feet. You can calculate now. But mind that convert 7 feet into inches, because L is in 7 feet. So it will be 78.72 into 4 divided by, it will be like this. The P value will be in kips.
Sir, 3.75.
3.7 kips. You should note down this value in your notes. Okay, we can write down P as P max. Okay, this is P max because it's the maximum load, this beam, which we at the moment are assuming is made of plain concrete. So you can write down P max. Okay, what will happen to a plain concrete beam if the value of P exceeds this P max? you know that the beam will fail. Okay? So you can calculate the maximum load carrying capacity of this. Let's say we are applying a uniformly distributed load on this beam. So that in that case, it will be WUL square by 8. And you can calculate WU also. Okay? WUL square by 8 in a similar manner. WUL square by 8 will be equal to 78.72, and you can calculate WU. So you can also calculate the maximum uniformly distributed load to which this beam can be subjected if it is made of plain concrete. So this was all about plain concrete. If you want to design a beam which is made of plain concrete without reinforcing bar, this is the procedure you can use for the design. Okay, let's talk about the different parameters which exist in the equation for MR. How can we increase MR is my next question. You can increase MR. It is very straightforward because MR is a function of size of the beam, BH, and also is a function of FT, and FT is further function of FC prime. So if you want to increase FT, you have to increase the concrete strength FC prime, isn't it? Or if you don't want to increase FT, you can also increase BH, but with the increase in H, there will be maximum increase in MR. So by increasing the depth of the beam, you can twice increase MR as compared to increase in B. So it is better to increase depth of the beam instead of increasing width of the beam in order to increase the resisting capacity, flexure resisting capacity of the beam. This all discussion is applicable if there is no reinforcement in the beam, it is made of plain concrete. Now, coming to reinforced concrete beam. Let's say there is a reinforced concrete beam. The same beam for which we have done all this calculation is made of reinforced concrete beam. And in the beginning, since there is no crack, the stresses in the beam, the stresses in steel are so small that ASFS, which will be tensile force being produced in the steel bar, can be ignored. So the same equation will apply. But now what will be the result? When P on the beam exceeds this value which we have calculated equal to 3.75 K, what will happen to the beam?
It will crack, sir.
The beam will crack. A crack will appear in the beam. So this is the reason that this bending moment which we have calculated in this equation, MR, this is also called as cracking bending moment, MCR. MCR. This is called cracking bending moment, cracking moment. Why this is called cracking moment? Because it is the bending moment. It is the flexural capacity of the beam. It is the flexural capacity of the beam given only by concrete, not by steel. Although it is a steel reinforced concrete beam, but this capacity has been calculated based on the tensile strength of concrete, not on the basis of tensile strength of steel. So this is called cracking moment. Why this is called cracking moment? Because if this M, which is applied bending moment, exceeds this value, if the applied bending moment exceeds this value, then a crack will appear in the beam. So you can exactly calculate the bending moment in advance at which a crack will be expected in the beam. This is another lesson that you learn from this discussion, that if you want to calculate the cracking bending moment capacity of a beam, you can do this in advance because you would know what is the strength of concrete, you would know the size of the beam, so you can exactly calculate the cracking moment capacity of a beam, which is the capacity at cracking, which is the capacity of the beam at cracking. And this capacity of the beam at cracking is contributed only by concrete and not by steel. And if the applied bending moment exceeds this cracking bending moment, then a crack will appear in the beam. Now, can you calculate this value? You have calculated this value MR equal to, for this beam, which is equal to 78.72 kip inch. Okay, and you also calculate the value of P, which is 3.75 kip. 3.75 kip. Calculate me this value in kilonewton. Calculate me, give me this value in kilonewton.
Sir, 16.65.
See? Yes, it's almost this value. Exact value, give me the exact value. P max equal to how much in kilonewton?
16.68.
16.65, sir.
Let's say it's approximately 17 kilonewton. Okay, 17 kilonewton. So what do we conclude from this discussion? That in that particular test that we have seen in the video, the first crack should have theoretically, at least theoretically speaking, should have appeared corresponding to a load value of 17 kilonewton. Is it correct?
Yes, sir.
Now recall the video. What was the first load that person who was watching the conducting the test rode over top of the crack? I will show you the video now once again.
Sir, 30 times.
Yes. Okay, so you have seen that the value is 30 kilonewton instead of 17 kilonewton. Can you tell me the reason for this? Can anyone of you tell me the reason?
Sir,
Please.
Sir, due to reinforcement, the value increase.
What is your name? What is
Ijaz
your name?
Ahmed, sir.
Ijaz Ahmed.
Ijaz
Yes.
Ahmed.
Ijaz Ahmed. So you are telling me the reason for this? What is the reason?
Sir, due to reinforcement, the value increases.
Because there is a component of reinforcement resistance also in terms of ASFS. Although we assume that F is equal to 0, there will be some value of ASFS coming from that. Okay, this is one reason. The other reason is that FC prime that we have used in our equation is 3000 psi, but it may not be true because the cylinder that we have tested, for example, may be weaker than the actual concrete being placed in the concrete beam. So FC prime actually placed in the beam might be greater than that. This can be a reason. Okay. The third reason can also be that the person who was noting down the cracks might have missed a very minor crack, which would have appeared as corresponding to 17 kilonewton. This can be another reason. Understand? Anyway, you can now from this discussion, which we have concluded in the corresponding to stage 1, you have learned how to calculate the flexural capacity of the beam if it is made of plain concrete, and if it is made of reinforced concrete, but we say that it is the cracking capacity of the beam or the capacity of the beam at cracking, and as soon as the applied bending moment exceeds the stressing bending moment, a crack will appear. Now let's say if there is a demand from someone and he asks us, because we are engineers, he asks us that I require a beam because there is a need. Okay, a person demands that I need a beam, reinforced concrete beam with no cracks at all, no crack. Even if it is a minor crack, I don't want even a single crack in the beam. So how should we design this beam? We should design this beam with these equations. With these equations will be used in the calculating the flexure capacity of the beam, and only then no crack will appear in the beam. However, if we do this, then you can see that the beam capacity comes out to be only 3.75 kip. The beam capacity comes out to be 3.75 kip, corresponding to this stage. Okay, you should note down this capacity, and we move ahead and we allow some cracking in the beam, and then calculate the capacity of the beam. If some cracks have appeared, we know that we have seen in the video that beam is not going to collapse even if it is cracked substantially, almost to half depth of the beam. The beam cracked, and the beam was still capable of taking more and more load, and the beam was out of any imminent collapse. The danger of collapse, though. So what we can do is that corresponding to another stage where we would allow some cracking of the beam, because we have seen that few cracks in the beam will not necessarily cause failure of the beam. So what will happen at that stage? What will happen at this stage? Let's discuss that stage number 2 now. But I will give you a 5 minutes break, only 5 minutes break, and then we will start discussing stage number 2. Okay. Okay, let's resume the lecture and start discussing stage number 2. In stage number 2, as we said earlier, that the stage number 2 corresponds to a stage where the beam on the tension side and the tension side is cracked, as you can see the cracks, and the steel is now entirely responsible for resisting tensile stresses. However, concrete is still intact on the compression side. So now the situation is such that the beam behaves like a composite beam. Composite beam is a beam made of two or more than two material. So this reinforced concrete beam, which was in the beginning behaving like a homogeneous beam made of only one material, now it's behaving like a composite beam, behaving like a beam made of two different material. So in the upper part of the beam, the concrete is resisting compression or compressive stresses. In the lower part of the beam, the steel is resisting the tensile stresses because concrete has cracked. And you know that no stresses can transfer across the crack. So stress transfer across the crack cannot occur. This can only occur if material is there. So steel material is there because steel being placed as reinforcing bar is being placed from one end to other end of the beam, and steel has not cracked. Steel has not cracked. Only concrete has cracked. So concrete is not capable of transferring stresses. Only steel is now taking all the stresses. Okay. So the situation is like this. There is no contribution coming from concrete now. All the contribution is coming from steel on the tension side. So the part of the equation which we were explaining or which we were deriving in the stage number 1, which was equal to MR equal to FT divided by FT into B square by 6. And that equation FT will become 0 when FT becomes 0. So contribution from concrete is 0. Contribution from concrete becomes 0. And ASFS will only be there. Okay. ASFS will be there. And okay. If we had to write this equation just like the previous equation, we should have written this equation like this: FT into B square divided by 6 plus ASFS, which is from steel. You know, P is S times A. I have said this few times. P, and this P for steel in tension will be T, S, T in steel, and S in steel is Fs, and area of steel bar is As. So basically this is Tc, which is the tension resisted by concrete, and this is Ts. In the previous case, we ignored contribution from steel, and we said that ASF, because Fs is very, very small, so this contribution is 0. Now, the stresses are not small. So ASFS will be contributing, but the tensile strength of concrete, which was equal to 0.4 KSI calculated in the previous case, has already exhausted because the concrete has cracked. So this FT is equal to 0 because there is no value of FT. So when FT is 0, this comes out to be 0. This will be 0. So if MR in the second stage, MR will be equal to ASFS. ASFS. It will be into lever arm. Into lever arm. This whole term into lever arm. ASFS into lever arm. Because this has already been multiplied with lever arm. So I will write this again so that you don't make any mistake. MR equal to FT BH square by 6 plus ASFS into lever arm. What will be the lever arm for this? If this is the centroidal distance from top, which will be D. And this distance, we know that this is, if the distance from the top to the neutral axis depth, the neutral axis depth in this case, you should also note down, is not h/2 now, because the neutral axis has shifted upward. The concrete has cracked on the tension side, so the neutral axis would have shifted upward. So this depth is not h/2. Let's say this depth is small c. So the distance from top fibers to this c will be c/3. This will be c/3. And this distance will be d minus c/3. If total distance from top is d, this will be d minus c/3. You will see this in the next slide. Anyway, this will be the equation now. So if this equation becomes, if this term becomes 0, then we will be left with mr is equal to ASFS into lever arm. Correct? And let's see what is this ASFS and what is this lever arm equal to. Okay, in stage number 2, you should note down few things. Stage number 2 is this stage where concrete is cracked on tension side, but concrete is still intact on the compression side. And on the tension side, now it is only steel, which is taking all the tensile stresses. So the situation will be like this. You should concentrate on this equation. Now this is the stress diagram, and this is strain diagram. In the stress diagram, if you look at the stress diagram carefully, the stage number 2 is a stage. We have chosen this stage. You should mind this also. Okay, that we have chosen this case for our discussion, that when the beam being loaded by a load P undergoes several stages before it finally collapses, we can choose a case such that this is the situation in that case, that the stress in concrete in the top fiber is equal to 0.45 Fc and stress in steel is 0.5 Fy, not equal to the yield. This is the situation at stage 2. Now, when this is the situation at stage 2, we can also calculate MR, resisting bending moment corresponding to this stage. But before we calculate MR, we should also focus on few more things. That when concrete in the top extreme fibers on the compression side is equal to 0.45 Fc, what is this value on the stress strain diagram? This value on the stress strain diagram is almost here. Almost here. This is Fc prime, so this is almost half of this. So there is still linearity. Concrete is still linearly proportional to strain. Stress in concrete is still linearly proportional to strain. So this can be represented like this. Up to 0.45 Fc prime, stress in concrete is still proportional to strain. But beyond this value in concrete on the compression side, the stress will no more be linearly proportional. It will be still proportional. You should note down these things. One is linear proportionality, and the other thing is non-linear proportionality. Linear proportionality means when we say that, you know that S is equal to E into strain, you know this, or S is proportional to strain. When strain is to power 1, if you make a plot between stress and strain, and this is linear, this is a line like this, linear relationship, this is called as linear proportionality, because S is, if we represent S by F, and this is by E, so stress is proportional to strain, linearly proportional. However, if this becomes a curve of second degree, third degree, or so on, then there is still proportionality, but F is proportional to E power 2, maybe E power 1.2, 1.3, 1.4, or 3, whatever it is, depending on the behavior of the material. It will depend on the behavior of the material. So stress is still proportional to strain in the case of concrete, but this proportionality is not linear. It becomes non-linear now. It becomes non-linear, and this value is almost equal to 0.45 Fc prime. From test, it has been confirmed that up to a stress value of 0.45 Fc prime for concrete, the stress is proportional linearly to strain. Okay. And this thing has been shown here in this equation. Okay, for steel, you know that up to the yield strain or the yield strength, stress is proportional to strain. So steel is also in the linear elastic stage. It is in the linear elastic. Okay, what is elasticity and linearity? Linearity, as I explained, just explained, elastic behavior is the behavior of a material which, when unloaded, will regain its original position after unloading. Like when you stretch a steel bar, but the stretching is below the yield limit, so it can completely recover its original length. This is called elasticity, because the behavior, the elasticity is the property of material, due to which it can regain its linearity, as I was just explaining, that if the behavior of a material is such that stress is proportional to strain, it can be linearly proportional, it can be non-linearly proportional. Linearly proportional is that it will give you a straight line. Non-linear proportionality means that it will give you a curved type of plot. Okay, and elasticity means that if when you remove the load, you can completely regain the original length of the material. So a material can be linear elastic in a linear elastic stage. Linear elastic stage mean that stress is proportional linearly to strain, and elastic means that it is in the elastic stage. It has not crossed the elastic limit, which means that if you unload the material, you will be able to completely regain the original length. So linear elastic is one stage, linear elastic stage. Then there can be a non-linear elastic stage. Non-linear elastic stage is a stage which means that stress is non-linearly proportional to strain, but the material is still in the elastic state, which means that if when you remove the load, the material can regain its original length, still can regain its original length. So this is non-linear elastic stage. Then you can have a linear inelastic stage. Linear inelastic stage is a state when stress is proportional linearly to strain, but when you remove the load, the material is not capable of regaining its original length. So a permanent set has occurred at some point in time. And there can be non-linear inelastic behavior. Non-linear inelastic. The stress is non-linearly proportional to strain, and the material behavior is also inelastic. So there are four possibilities: linear elastic, non-linear elastic, linear inelastic, non-linear inelastic. Okay, so at this stage, concrete on the compression side is in linear elastic stage, steel on tension side is in linear elastic stage, but concrete on the tension side has crossed its elastic limit as well as its a linear limit, and concrete has completely cracked on the tension side. So there is no contribution from concrete on the tension side. Now we can write down the equations like this. For MR, resisting moment. MR will be equal to, under this condition, MR will be equal to, because we should write down MR in terms of T times lever arm, and this, if this is C, and we have a T here, and this is the total, this is the effective depth, which is the depth of a steel bar. It is the distance from top of the concrete beam to the centroidal axis of the steel bars. This is called D. This distance will be, if this depth of the neutral axis is now small c, this depth is not h by 2. This is small c. This is c, but this will be c by 3. So this depth will be d minus c by 3. D minus c by 3. Correct? So MR will be equal to T into D minus C by 3. And you know that T is equal to AS Fs, and Fs was equal to 0.5 Fy, 0.5 Fy. So this will be AS and 0.5 Fy d minus C by 3. Mr will be equal to 0.5 AS Fy d minus C by 3. Now we can calculate resisting bending moment, flexure capacity corresponding to stage 2. This is stage 2 flexure capacity. The only problem is now that you do not know AS and you do not know C, this small c, which is the neutral axis depth. However, if we equate this point, if we equate Mr to M, if we equate this Mr to M, which was applied bending moment, we can calculate A is required in order to resist the applied bending moment. This will be the amount of steel required to resist the bending moment. How can we do this? This Mr, if we equate this Mr to applied bending moment, which was coming from P, PL by 4, or WL square by 8. So this Mr will be equal to 0.5 AS Fy d minus C by 3 equal to M. You can calculate required AS, which will enable the beam to resist this M, which is coming from the load. This M divided by 0.5 Fy d minus C by 3. So this we can call as equation number 1. Because this is the S which, when placed, this S will be calculated from this M, which is coming from load P. When this AS is placed inside the beam, then the beam will not fail. Corresponding to stage number 2. Corresponding to stage number 2, the beam will not fail. So you can also realize that the definition of failure is different in different stages. In stage number 1, we call failure to the appearance of the crack. In stage number 2, we will call failure to a situation where Fs is more than 0.5 Fy and Fc is more than 0.545 Fc prime. But if we calculate AS corresponding to stage number 2, this is not going to happen. This will not happen. So the actual failure is different from what we are discussing right now in these different stages. In stage 1, we said that the beam will be said to have failed if a crack appears in the beam. Okay, because all the equations corresponding to stage 1 were based on the appearance of the crack. Here is stage number 2, the cracks have already appeared, but we say that the stress in steel should not be more than 0.5 Fy, and the stress in concrete on the compression side shall not be more than 0.45 Fc prime. So if we derive the equations based on these assumptions, then it will be for sure that Fs in steel will not be more than 0.5 Fy, because we are calculating AS based on this 0.5 Fy and based on the AM applied bending moment. So Fs in steel will always be less than the yield, and stress in concrete will always be less than Fc prime, 0.45 Fc prime. Okay, but the problem in this is that there is a C in denominator, which is the neutral axis depth, and this is not known to us. This C is not known to us. How can we calculate this C now? How can we calculate this C? We know that for couple to exist, C must be equal to T. This C must be equal to T. Because if C is not equal to T, then the basic requirement of equilibrium will be compromised. So C is equal to T. You know that C is equal to, from the top, it is Fc plus 0 divided by 2, because we were taking every stress, and then B is the width of the beam, and C is the neutral, small c is the neutral axis depth, and this is equal to ASFS. Now you know that Fs is equal to 0.5 Fy and Fc is equal to 0.45 Fc prime. You substitute these values now. 0.45 Fc prime divided by 2 into B into C is equal to AS into 0.5 Fy. And calculate C from this now, small c. Small c. Small c will be equal to, from this equation, because this is Fy by 2, this is Fy by 2. So this 0.5 will be cancelled with this 2. Correct? And we will be left with AS Fy divided by 0.45 Fc prime B. But again, there is a variable AS which is not known to us. This is equation number 2. Now, what can we do? Either we substitute this value of C of this equation in the equation number 1, and finally we will end up in a quadratic equation, quite complicated. But instead of that, we can also use a very simple procedure which is called a trial and success method. In the beginning, in the equation number 1, you assume the value of C. You know that the total depth of the beam in our previous case, in the test case, was 12 inch, and half depth is 6 inch. So the value of C will certainly be less than 6 inch, because the value of half depth is 6 inch. So C will be 4 or 5 inch. So let's say you assume a value of C equal to 4 inch. And you, because M is applied bending moment, and it will be known to us because it will come from bending moment. So for C is equal to 4 inch, you calculate AS, because everything else is known to you. And then this AS, calculated AS, substitute this value in equation number 2, because this AS is now known to us, and calculate C. And once you calculate this C, substitute this calculated value of C in the equation number 1 again for C here, and recalculate AS. And the recalculated value of AS again substitute in this equation number 2 here, and recalculate C, and run this cycle. After a few cycles, the values of AS and C will not change. That will be the required AS for that particular situation. Now I will give you just one simple example, okay, which we will correlate, which we will be trying to correlate with the previous case, okay. Okay, let's say the applied bending moment is 500 inch kip. M is 500 inch kip. Can you do the trials now? With C equal to 4 inch, calculate AS.
सर ये आपने कितना बताया सर?
500 kip inch. Fy, the value of Fy you can take is 60 KSI, okay? Fy, you can take is 60 KSI. And D value, the total depth was 12 inch. The D value you can take as 9 inch. Effective D you can take as 9 inch. Okay. FC value you should use in KSI. Okay, this will be 3 KSI. FC is equal to 3 and Fy is equal to 60. You will be careful with the units. Okay. Any result from this? The C value, I think this M value is very high for this beam. So we can reduce this M value a little bit so that the values converge. I will tell you the reason for this not converging at some other time. But if you reduce the value of M, because the beam is a very small section, and this value of M is very large, 500 HK, if we reduce this value to 200 HK, then the values will converge. So take the value of M equal to 200 HK instead of 500 HK. Okay?
Yes, sir. Yes, sir.
Now, tell me what is the value of AS when M is 200 inch kip, 200 divided by 0.5 divided by 60 into D 9 minus, let's say C is initially 3 inch. This will be 8. Okay. What is the value for first trial?
0.869.
AS is equal to how much?
0.869.
0.869.
FC तो 4 आपने गिवन किया।
FC प्राइम तो 3 के ऐसा ही है ना। मैंने सिर्फ M की वैल्यू चेंज कर दी क्योंकि M बेंडिंग मोमेंट बहुत ज्यादा है और ये जो बीम हम डिजाइन इस वक्त कर रहे हैं इसकी डेप्थ और वेट इतनी ज्यादा नहीं है कि ये इस बीम में ये वैल्यू AS और C की वैल्यू कन्वर्ज हो जाए। ये भी एक टेस्ट होता है कि जब आपकी M की वैल्यू बहुत ज्यादा हो तो फिर इसका आप इस तरह कर, हम M तो प्रैक्टिकली वी कैन नॉट डिक्रीज M क्योंकि M तो इज कमिंग फ्रॉम ए लोड, तो हम बीम की डेप्थ और वेट को बढ़ाएंगे। लेकिन मैं अभी चाहता हूं कि बीम की डेप्थ और वेट को हम न बढ़ाएं और हम उसी बीम को इस्तेमाल करें जो बीम हमने अभी टेस्ट में टेस्ट किया है, तो उस बीम को हम इस्तेमाल करें जिसकी विड्थ 8 इंच है और डेप्थ उसकी टोटल डेप्थ 12 इंच है और इफेक्टिव डी उसकी 9 इंच मैंने एज्यूम की है।
सर C 4.82 आ गया है सर।
C कितना आ गया?
4.82।
4.82। अभी C की वैल्यू दोबारा उधर आप डाल देंगे। अच्छा, इस तरह जब आप ट्रायल करते जाएंगे ना तो फाइनली यू विल गेट ए वैल्यू ऑफ AS which will no longer change and then that value of AS can be selected as your final AS value। अगर आप इस एक दफा फिर ट्रायल करें तो बस ये फिर चेंज नहीं होगा। आप C 4.82 से तरह मालूम करें कितनी वैल्यू AS की आ रही है। 0.9 AS is coming, AS 0.9 स्क्वायर इंच आ रही है नेक्स्ट ट्रायल से। और अगर आप C मालूम करें तो C तकरीबन उतना ही होगा जो आपने 4.9 हो, 4.85 है इतना 5 इंच। जस्ट अनदर ट्रायल, एक और ट्रायल कर लें विद C इक्वल टू 5 इंच। तो अगेन इट कम्स आउट टू बी 0.91 कर लें।
C5 आ गया सर।
ठीक है जी, हाँ जी,
C5 आ गया सर।
हाँ बस आ गया। अब देखिए व्हाट इज द कंक्लूजन फ्रॉम दिस होल डिस्कशन। कंक्लूजन इस डिस्कशन का ये है, पहले आपके पास M कितना था स्टेज नंबर 1 में, मैक्सिमम M that could be resisted by the beam without reinforcement।
तो 78.72 समथिंग।
अच्छा, ये कितना 200 कितना बढ़ गया? ये तकरीबन 2.5 टाइम्स बढ़ गया ना बेंडिंग मोमेंट।
जी सर।
ठीक है ना? मतलब ये है, देखें फाइनली मतलब ये है कि अगर आप 0.91 स्क्वायर इंच की रिइंफोर्समेंट बीम के अंदर डाल दें जो कि बहुत कम रिइंफोर्समेंट है, तो आप बीम की कैपेसिटी को 2.5 टाइम्स बढ़ा सकते हैं। लेकिन इस शर्त पर कि बीम में कुछ क्रैक आएंगे, बट द क्रैक्स विल नॉट बी विजिबल। क्रैक्स जो है हियर लाइन क्रैक्स होंगे। दिस इज द कंक्लूजन फ्रॉम दिस डिस्कशन, that if you design your beam corresponding to stage number 2, you can increase the capacity of your beam flexure capacity almost 2.5 to 3 times or even more, depend करता है कि आप कितना मैक्सिमम AS डाल सकते हैं। AS जब आप बढ़ाते जाएंगे तो उसके साथ कैपेसिटी भी बढ़ती जाएगी। But this is for sure that substantial improvement in the flexural capacity of the beam is possible if it is reinforced with the reinforcing bars, And that's true. The stress in steel is not being taken to the yield strength. ये भी आप नोट करें कि इस स्टेज पर जब हम डिजाइन कर रहे हैं तो हमने देख लिया कि 0.91 या 1 स्क्वायर इंच, जो कि इतना ज़्यादा स्टील नहीं है, अगर हम बीम के अंदर नीचे डाल दें तो हम 2 से 3 टाइम्स तक अपनी बीम की कैपेसिटी, फ्लेक्सर कैपेसिटी बढ़ा सकते हैं, जो कि बहुत अच्छी चीज़ है। यानी हम ज़्यादा पैसे नहीं खर्च कर रहे हैं। लेकिन अगर आप रिइंफोर्समेंट नहीं डालते हैं और आप कहते हैं कि मैं कैपेसिटी को बढ़ाना चाहता हूं, तो आपको बीम की डेप्थ बढ़ानी पड़ेगी, आपको बीम की वेट बढ़ानी पड़ेगी, आपको कंक्रीट की स्ट्रेंथ बढ़ानी पड़ेगी, करिस्पॉन्डिंग टू स्टेज नंबर 1 की बात अगर आप करें तो इंस्टेड ऑफ इंक्रीजिंग द वेट एंड डेप्थ एंड कंक्रीट स्ट्रेंथ, जस्ट प्लेसमेंट ऑफ 1 स्क्वायर इंच, सिर्फ 1 स्क्वायर इंच का स्टील आप जब नीचे डाल देंगे तो आप 2 से 3 टाइम्स आप अपनी बीम की कैपेसिटी को बढ़ा सकते हैं। समझ गए आप इस बात को? And the importance of reinforcement. ठीक है जी।
लास्ट में नहीं सर, कैसे 1 इंच लगाएंगे तो कैपेसिटी ज्यादा होगा सर?
जी किस तरह, दोबारा बताएं
सर। स्टेप पे नहीं समझा सर, 1 इंच कैसे नीचे रखेंगे स्टील को?
हमने देखें, हमने बेंडिंग मोमेंट M 200 इंच की लिया ना।
जी सर।
अब आप इस तरह करें कि आप 200 इंच की न लें, आप MR मालूम करें बाय एज्यूमिंग A is equal to 0.9 या 1 स्क्वायर इंच। आप MR मालूम करें कितनी आपके पास आ रही है MR। ये तो MR की इक्वेशन आपके पास है ना, ये नीचे जो इक्वेशन मैंने लिखी है, दिस इक्वेशन फॉर MR, यू एज्यूम दैट योर A will be equal to 1 स्क्वायर इंच, और आप इस 1 स्क्वायर इंच से आप C मालूम करें इस इक्वेशन नंबर 2 से। 1 मल्टीप्लाई बाय 60 डिवाइड बाय 0.45 मल्टीप्लाई बाय 3 एंड मल्टीप्लाई बाय 8, इससे आप C मालूम करें। उस C को आप इक्वेशन नंबर इसमें डालें MR की इक्वेशन में, तो आप कैपेसिटी मालूम करेंगे। आप अपनी बीम की कैपेसिटी को इस तरह बढ़ा सकते हैं, जब आप नीचे AS डाल देंगे 1 स्क्वायर इंच, तो फिर आप अपनी बीम की कैपेसिटी को, इस कैपेसिटी को आप समझ गए?
यस सर, अब समझ गए सर।
अब समझ गए आप?
सर
जी प्लीज।
सर इसकी वजह से सर बीम में क्रैक नहीं है, क्योंकि कंक्रीट की जो कैपेसिटी थी सर तो क्रैक होगी सर।
हाँ, वो तो मैंने कह दिया ना कि हम क्रैक्स अलाउ करेंगे, लेकिन क्रैक्स इतने हेयरलाइन क्रैक्स होंगे कि वो नजर नहीं आएंगे। अगर आप उसको मैग्नीफाइंग ग्लास,
तो स्टैटिक तो खराब नहीं होगा सर?
नहीं, आपको नजर नहीं आएंगे तो कैसे खराब होगा?
ठीक है,
नजर तो नहीं आएंगे ना आपको। आप मैग्नीफाइंग ग्लास से तो हर वक्त बीम को नहीं देखेंगे ना।
ठीक है सर।
ओके सर।
The cracks will not be visible. There will be hairline cracks. ठीक है, हेयरलाइन क्रैक्स होंगे, विजिबल क्रैक्स नहीं होंगे। तो फिर ये रिइंफोर्समेंट का फायदा है। ये रिइंफोर्समेंट जो हम इस्तेमाल करते हैं ना, वी से दैट रिइंफोर्स्ड कंक्रीट इज बेटर देन प्लेन कंक्रीट। तो आपने इसका फायदा देख लिया कि सिर्फ 1 स्क्वायर इंच AS डालने से हमने बीम की कैपेसिटी कितनी बढ़ा ली। अगर आप AS को थोड़ा और बढ़ा दें तो बीम की कैपेसिटी को आप और बढ़ा दें, लेकिन इट हैज ए सर्टेन लिमिट, उससे ज्यादा फिर आप इस कैपेसिटी को बढ़ा नहीं सकते। ओके, this is the advantage that I was trying to explain to you, the advantage of reinforcement, but this is just at stage 2. ये stage 2 में बार बार इसलिए कहता हूं कि हमने दो चीजें इसमें की हैं जो आपको जिसकी तरफ आपको तवज्जो देनी चाहिए। 2 things that we have done in this stage number 2 to which you should pay attention, that is that FS in steel we have kept equal to 0.5 FY। इसका ये मतलब है कि हमने स्टील की फुल कैपेसिटी को यूटिलाइज नहीं किया है। मैं ठीक कह रहा हूं?
जी सर।
स्टील की फुल कैपेसिटी को हमने, क्योंकि हम स्टील को 0.5 FY, हालांकि स्टील में तो ताकत है अभी, इट कैन गो टू यील्ड स्ट्रेंथ, लेकिन हमने इसको यील्ड स्ट्रेंथ तक नहीं ले जाने दिया। एंड द कंक्रीट कैन आल्सो गो टू FC प्राइम, बट वी हैव केप्ट दिस इक्वल टू 0.45 C प्राइम। नाउ लिसन टू द कंक्लूडिंग स्टेटमेंट। This is a procedure of design which we call as working stress design or allowable stress design. इसमें हम क्या करते हैं? In this method, we reduce the strength of material. We have reduced the strength of steel by 50%, and we have reduced the strength of concrete by almost 55%. So that is 0.4, almost 50%. Okay, so we have reduced the strength of concrete and steel by 50%. हाफ स्ट्रेंथ हमने लिए हैं, और हमारा जो लोड है अप्लाइड PL/4, वी हैव डन नथिंग टू दैट लोड. हमने जितना लोड है बस उसके मुताबिक बेंडिंग मोमेंट हमने मालूम कर लिया, लेकिन स्ट्रेंथ हमने कम कर लिए. तो इसमें फैक्टर ऑफ सेफ्टी आ गया 2 का, क्योंकि जब मैं कहता हूं कि बीम में अगर देखें, फॉर दिस बीम if the value of mx if the value of m applied exceeds this mr, तो हम theoretically कहेंगे कि बीम फेल हो गया, लेकिन एक्चुअली तो बीम फेल नहीं होगा ना. बीम तो भी काफी मजीद लोड भी ले सकता है, और आपने देखा कि उसमें तो काफी स्टेजेस और भी हैं. बट फॉर द सेक ऑफ theoretically speaking, we will say that the beam has failed corresponding to stage number 2. स्टेज नंबर क्यों फेल हो गया? क्योंकि स्टील में स्ट्रेस 0.5 FY से बढ़ गया और कंक्रीट में स्ट्रेस 0.45 C' से बढ़ गया. तो हम इसको कहते हैं कि बस ये फेल हो गया, क्योंकि हमने इस बेसिस पर ये सारी डेरिवेशन की है कि हम कहते हैं कि स्टील में स्ट्रेस 0.5 FY से नहीं बढ़ेगा और कंक्रीट में स्ट्रेस 0.45 C' से नहीं बढ़ेगा. दिस इज द रिक्वायरमेंट ऑफ स्टेज नंबर 2. सो दिस विल गिव अस अ फैक्टर ऑफ सेफ्टी ऑफ 2, एग्जैक्टली 2, क्योंकि आगे आपके पास मजीद 0.5 FY स्टील में भी मौजूद है और 0.45 FC' कंक्रीट में भी मौजूद है. तो आपके मतलब ये है कि हमारे पास हाफ कैपेसिटी भी मौजूद है. तो ये हाफ कैपेसिटी जो है ये सेफ्टी फैक्टर के तौर पे यूटिलाइज हो जाएगी. ये मेथड जो हम ये अब डिस्कस कर रहे हैं स्टेज नंबर 2 पे, तो ये अलाउएबल स्ट्रेस मेथड या वर्किंग स्ट्रेस मेथड कहलाता है. और काफ़ी 30-40 साल पहले इस मेथड पर हम डिज़ाइन करते थे. मैंने तो खुद डिज़ाइन नहीं किया, लेकिन हमसे पहले इन 1970s this method was used for the design of reinforced concrete beam. But this method is no more used for the design of reinforced concrete beam. The method that we will be discussing in stage number 3 is used for the design of beam, which is much more economical than the stage number 2 method, and even more than the stage number 1. Stage number 1 तो बिल्कुल ही एक ऐसा मेथड है जिस पे आप क्रैक ही अलाउ नहीं करते. तो आप फाइनली यू विल बी इन पोजिशन टू सी व्हाट हैपेंस फाइनली, कि आप अगर बीम में क्रैक अलाउ नहीं करते हैं तो आपको एक बहुत बड़ा बीम डिजाइन करना पड़ेगा. और अगर आप बीम में क्रैक अलाउ करते हैं, हेयर लाइन क्रैक, और थोड़ा सा रिइंफोर्समेंट डाल लेते हैं, तो आप बीम के कम सेक्शन से भी ज्यादा कैपेसिटी ले सकते हैं. और वो स्टेज नंबर 2 की भी मैं बात कर रहा हूँ. लेकिन स्टेज नंबर 3 पे जब आप जाएंगे तो आप मजीद कैपेसिटी को यूटिलाइज कर सकते हैं. लेकिन द डिफरेंस बिटवीन स्टेज नंबर 2 and 3 will be that in stage number 3 we will be fully utilizing the strength of steel and concrete, but at the same time we will be slightly increasing the demand M. So introduce factor of safety in our designs. If you remember, in the previous lecture I was telling you that there are 2 methods of design: working stress method and strength design method. In working stress method, the strength of material are reduced by half, but the applied bending moment is not increased or not amplified. In the strength design method, on the other hand, the strength of material are not reduced, but the applied bending moment is increased a little bit in order to introduce some factor of safety in our design. So this is the difference. We will discuss stage number 3 in the next lecture. We cannot discuss this. This is enough for today. You go through all these slides and these concepts and come up with questions in the next lecture. In the next lecture, then we will start discussing stage number 3, and we will be designing our beams corresponding to stage number 3. We have discussed these stages 1 and 2 for the reason that it will help you developing your concept in reinforced concrete design, and some of these concepts are then used in certain situations. So you will be able to use these concepts in those situations where these equations are required corresponding to stage 1 and 2. However, in this course, RCD 1 will be frequently referring to stage number 3, and we will be designing our beams corresponding to stage number 3, which we will discuss in the next lecture. Now, this is the end of the lecture. If you have any question, you can ask your questions, please. Any question? Any question?
एक्सक्यूज मी सर. सर जब हम टेंशन में हमारे पास जब बिल्कुल बॉटम पे उसके क्रैक अपीयर हो जाता है, तो जो फोर्सेस उस पे अप्लाई हो रही हैं, क्या वो उससे ऊपर वाले फाइबर्स पे शिफ्ट हो जाती हैं?
हाँ बिल्कुल, क्योंकि देखें, आप अगर किसी मटेरियल में गैप आ जाए ना, क्रैक तो गैप का नाम है ना, तो उसके अक्रॉस तो कोई स्ट्रेस ट्रांसफर नहीं हो सकता ना। तो इसका मतलब है कि बीम की जो इनिशियल डेप्थ एच हमने ली हुई थी ना, अगर हम ये प्लेन कंक्रीट की बात करें तो प्लेन कंक्रीट पे नीचे का कंक्रीट गया, बस खत्म हो गया। अब ऊपर का जो कंक्रीट है ये क्रैक से ऊपर ऊपर वो रेजिस्ट करेगा। इस तरह न्यूट्रल एक्सिस ऊपर शिफ्ट होता जाएगा, क्रैक जैसे जैसे ऊपर चलता जाएगा, चढ़ता जाएगा, तो न्यूट्रल एक्सिस की डेप्थ भी कम होती जाएगी, और बीम का जो सेक्शन जो एक्चुअली रेजिस्ट करेगा वो सेक्शन होगा जो क्रैक से ऊपर है। क्रैक से नीचे का सेक्शन तो रेजिस्ट ही नहीं कर सकता है। लेकिन अगर इसमें रिइंफोर्समेंट हो तो फिर रिइंफोर्सिंग बार जो कि स्टील के, जो कि कंक्रीट के साथ प्रॉपर्ली बॉन्डेड है, वो तमाम स्ट्रेस को, टेंसाइल स्ट्रेस को ले लेगा और कंक्रीट ऊपर के कंप्रेसिव स्ट्रेस को ले लेगा। आई होप आई हैव आंसर्ड योर क्वेश्चन।
सर टेंसाइल फोर्सेस की हमने बात की थी कि वो ख़त्म हो जाते हैं, इस वजह से हमें रीइंफोर्समेंट प्रोवाइड करनी पड़ती है। तो अगर वो ऊपर वाले फाइबर्स में शिफ्ट होते हैं तो फिर हम टी की वैल्यू को कैसे कहते हैं कि वो विदाउट रीइंफोर्समेंट खत्म हो जाएगी अगर क्रैक्स आ गए तो?
दोबारा आप क्वेश्चन करें, दोबारा क्वेश्चन करें, आहिस्ता आहिस्ता बोलिए।
सर मैं ये पूछ रही हूँ कि हमने कहा था कि जो रेजिस्टिंग हमारे पास फोर्स है वो टी है, और वो हमारे पास सेकंड स्टेज में जो है वो ख़त्म हो जाएगी क्योंकि क्रैक अपीयर हो गए हैं, तो रीइंफोर्समेंट जो है वो रेजिस्टिंग टेंसाइल फोर्स प्रोवाइड करेगा।
बिल्कुल बिल्कुल।
तो ये फिर ये हमने किस तरह कहा है कि वो बिल्कुल खत्म हो जाएगा जबकि वो ऊपर वाले फाइबर्स में शिफ्ट हो जाता है?
नहीं, ऊपर वाले फाइबर में तो न्यूट्रल एक्सिस शिफ्ट होने का मतलब ये नहीं है कि एफटी ऊपर शिफ्ट हो जाएगा। न्यूट्रल एक्सिस ऊपर शिफ्ट होने का मतलब ये है कि कंप्रेशन जोन अब स्क्वीज होना शुरू हो जाएगा। वो स्क्वीज हो रहा है ना, लेकिन नीचे का पार्ट जो सारे का सारा टेंशन में है। अगर आप स्ट्रेन डायग्राम देखें ना, तो स्ट्रेन डायग्राम में आप इसको जरा, मैं स्ट्रेन डायग्राम से आपको बताता हूँ। असल में होगा क्या, इनिशियली अगर मेरे पास ये स्ट्रेन डायग्राम है, इनिशियली बिल्कुल स्टेज नंबर 1 पे, जो कि मिड डेप्थ पे आपका न्यूट्रल एक्सिस आ रहा है, और मैं इसको ऐसे मिड डेप्थ पे लगा दूं, तो आपका जो नेक्स्ट स्टेज होगा स्ट्रेन का, वो ऐसे होगा कि ये न्यूट्रल एक्सिस थोड़ा सा ऊपर शिफ्ट हो जाएगा। ये मिड डेप्थ का लोकेशन है। अच्छा, न्यूट्रल एक्सिस बिल्कुल स्टेज नंबर 1 पे ये तो कोइंसाइड करेंगे, लेकिन आगे और आपका जो नीचे स्ट्रेन है ये बढ़ते जाएंगे ऐसे। फिर आपका जो नेक्स्ट स्टेज होगा वो ऐसे होगा कि ये और ऊपर शिफ्ट हो जाएगा, ऐसे होगा। अब ये पार्ट जो टेंशन में है ना, ये सारा जो टेंशन में पार्ट है, तो इसमें ये पार्ट भी टेंशन में है, ये पार्ट भी टेंशन में है, ये पार्ट सारे सारा पार्ट टेंशन में है इस लोकेशन तक, इस लोकेशन तक, ठीक है। और ये लोकेशन जो है ये तो क्रैक हो चुका है, इधर क्रैक आ गया, ये तो सारे का सारा क्रैक हो चुका है। तो अब ये थोड़ा सा पोर्शन जो हमारे पास कंक्रीट का अभी भी इधर पोर्शन में ये अनक्रैक्ड पोर्शन मौजूद है हमारे पास, ये पोर्शन, क्योंकि इसमें स्ट्रेंथ बहुत कम है, इधर स्ट्रेंथ बहुत कम है न्यूट्रल एक्सिस से, तो हो सकता है कि इधर क्रैक अभी ना आए हों, लेकिन नीचे का जो पोर्शन है ये क्रैक हो चुका है, ये क्रैक पोर्शन, और इसमें स्टील पड़ा हुआ है। अब हम कहते हैं इस पोर्शन को तो हम बिल्कुल इग्नोर कर लेते हैं, क्योंकि बहुत थोड़ा सा पोर्शन ऊपर रहता है, ये पोर्शन सारा क्रैक हो चुका है। इधर हम कहते हैं कि ये टी ही हमें सारे का सारा देगा, इस वक्त जो रेजिस्टेंस है वो टी देगा, ठीक है जी।
ये सर ठीक है।
ये जो आपकी बात इस हद तक सही है कि ऊपर जो पोर्शन है न्यूट्रल एक्सिस से बिल्कुल करीब करीब जो टेंशन जोन है, इसमें जो एफ टी होगा, हो सकता है कि ये एफ टी अभी एफ जो एफ आर है मॉडुलस ऑफ रप्चर 7.5 सी प्राइम उसको क्रॉस न कर चुका हो। ये आपकी बात सही है कि ये न क्रॉस कर चुका हो, और नीचे वाला तो क्रॉस कर चुका हो, तो इसको हम क्यों नहीं लेते हैं? तो इतना छोटा पोर्शन है कि इसको हम अगर ले भी नहीं तो इसका इतना इफेक्ट नहीं होगा इस तो पूरे कैलकुलेशन में, लेकिन ऐसी इक्वेशन को कॉम्प्लिकेटेड बना देगा, उसका कोई फायदा खास नहीं होगा। स्पेशली जब हम स्टेज नंबर 3 की बात करते हैं तो उस पर तो उसका कुछ भी इफेक्ट नहीं होगा। स्टेज 2 में तो हो सकता है कि थोड़ा बहुत इफेक्ट हो, लेकिन अगर आप इस वैल्यू को T इज इक्वल टू ASFY जो कि 0.5 ASFY से आप मालूम करेंगे ना, और इसको आप इस वैल्यू के साथ जमा करेंगे जो आपके पास इस छोटे से पोर्शन में है, तो ये ऐसे हो गए जैसे ये वैल्यू 100 है और ये वैल्यू 1 है या 2 है, तो इसका कोई फाइनल इंपैक्ट नहीं होगा रिजल्ट आंसर पे, सब्सटेंशियल इंपैक्ट नहीं होगा, ठीक है जी।
यस सर, थैंक यू।
एनी अदर क्वेश्चन? I can give you 5-10 minutes if you want to ask questions. It is good to ask questions at this stage because you are going to develop your concepts. So any question that arises in your mind, you can ask questions, please. Please ask questions.
सर ये जो हमारे फ्रेम स्ट्रक्चर में अगर हम बीम को यूज नहीं करते तो हमारे लोड ट्रांसफर मैकेनिज्म में क्या सर फर्क पड़ता है सर?
हमारे लोड ट्रांसफर मैकेनिज्म में फर्क ये पड़ेगा कि स्लैब डायरेक्टली जो है कॉलम को लोड ट्रांसफर करेंगे, बस इसमें तो और कुछ नहीं होगा। मतलब बेंडिंग मूवमेंट जो पहले बीम में आ रहे थे ना बिटवीन द कॉलम्स, वो तमाम बेंडिंग मूवमेंट स्लैब खुद ले लेगा और उसको फिर ट्रांसफर करेगा नीचे कॉलम्स को। पहले अगर बीम मौजूद थे तो असल में ये मैं किसी और लेक्चर में आपको एक्सप्लेन कर दूंगा कि बीम असल में उधर एक स्टिफनर के तौर पे काम करता है, यानी स्लैब की थिकनेस उधर हम ज्यादा कर लेते हैं जिसको हम बीम कहते हैं। तो वो बेंडिंग मूवमेंट को कलेक्ट कर लेता है स्लैब से और वो कलेक्टेड बेंडिंग मूवमेंट आगे पर ट्रांसफर करता है। इट आल्सो कलेक्ट द लोड्स, इट आल्सो कलेक्ट्स द बेंडिंग मूवमेंट एंड ट्रांसफर इट टू द कॉलम्स। सिर्फ उसमें ये होगा कि जब आप डायरेक्टली स्लैब को कॉलम के ऊपर रखते हैं तो स्लैब की थिकनेस चूंकि कम होती है तो कॉलम उसमें एक सुराख बना सकता है जिसको हम पंचिंग कहते हैं। तो उसके लिए फिर पंचिंग के लिए आपको डिजाइन करना पड़ता है उसको। जिस तरह के पीस ऑफ पेपर को अगर आप पेपर पिन्स के ऊपर रख दें और उस पीस ऑफ पेपर में आप कुछ सेंड डाल दें, सेंड ग्रेन्स, तो क्या होगा कि वो हो सकता है कि पेपर पिन उसमें सुराख कर लें। लेकिन अगर आप पीस ऑफ पेपर को मोटा कर दें, यानी कोई कार्डबोर्ड वगैरह ले लें या आप नीडल के उसके हेड्स को थोड़ा मोटा कर दें या नीडल्स को मोटा कर दें, तो फिर उसमें सुराख नहीं बना सकता है। ठीक है, तो इस तरह से सिर्फ ये नुकसान होगा कि अगर आप डायरेक्टली स्लैब को कॉलम के ऊपर रेस्ट करने की कोशिश करेंगे तो फिर आपको इस चीज का ख्याल करना पड़ेगा, और तो कोई मसला नहीं है।
ओके सर।
Anything else? Any other question? Okay, if there are no more questions, then it is the end of the lecture. Next time, inshallah, we will be discussing stage number 3. And I would like that you write down and prepare some notes. We don't have very clear slides for these two stages, stage 1 and 2. So if one of you could do these equations and these examples in some of the slides, we can make those slides part of our presentation. Because yesterday I was thinking that although we explain these things in the lecture, but we don't have very clear slides for these equations and calculations. So if some of you can do this, we'll be very happy to make those slides as part of our presentation in stage 1 and stage 2. And starting from the, basically what I want to do is that we should link these equations and the derivations with the video that we have watched, because the video gives us a very good reference or benchmark that we can use in stage 1, 2, and 3, so that we can prove that plain concrete, if we use plain concrete in our designs, it will be very, very uneconomical. And if we use reinforced concrete, it will be economical, and it will increase manyfold the flexure capacity of the beam. So I was just trying to link these stages with the beam that we have tested and that we have watched in the video. The beam size was 8-inch and 12-inch, and the beam was 7 feet long. So if we can calculate the capacity P of the beam corresponding to stage 1, where it is almost a case of plain concrete, then we can also calculate this capacity corresponding to stage 2, and then we corresponding to stage 3. So we will be in very good position, and it will clearly tell us the advantage of reinforced concrete, that if you place very nominal amount of reinforcement inside plain concrete, so that to make it reinforced concrete, you can manifold increase the flexure capacity of the beam as compared to the plain concrete. So if you can, if you understood today's lecture, and if you are able to design and to make few slides on the pattern of our slides, and you can share it with my TA before the next lecture, before the end of this week, so that we can make these slides part of our this lecture number 2. So we'll be very happy to do this. Okay. Okay. Thank you very much for the office. Assalamu alaikum.